Good day everyone, we are Group B and today we will be presenting our project titled Detection of Weak Vibration using Laser Optic and Photodiode under the guidance of Professor Sip Krishna Gopal. The objective of this experiment to determine the small vibration amplitude, determine vibration frequency using light displacement on photodiode, to verify the vibration amplitude using different frequency and different screen distance. The abstract. First is the purpose, to detect very small vibration using optical method. Second is method, use laser light and photodiode. Apply signal processing to improve sensitivity. And last is the outcome, detect weak vibration accurately. Offer a cheaper, non-contact alternative to standard sensor. Why it matters? Weak vibration can disturb sensitive system. Detecting them helps in physics experiment, engineering diagnostic, and structural monitoring. Current method, contact sensor like accelerometer are common, but they can affect the system and the sensitive to noise. Our approach, using laser optic and photodiode, which is non-contact, highly sensitive and immune to interference. Goal of experiment is build an optical setup, track laser reflection change from vibration, analysis photodiode signal to measure vibration. So this is our schematic diagram. For experiment setup, we will use connecting wires, resistor, loudspeaker, wooden stick, retard stand, wide form board, multimeter, oscilloscope, signal generator, power supply, photodiode sensor, laser pointer, and breadboard. Next, we will set up the experiment. Secure the seesaw-like platform on the stable surface. Attach a small mirror flat on the right end of the seesaw. Direct the red laser beam onto the mirror. Ensure the reflect beam reach the photodiode position on the screen. And position a speaker at the left end on to introduce vibration. Next is calibration and initial measurement. Align the laser beam for the stable initial reflection. Record the initial laser reflection position on the photodiode without vibration. Set up the reference screen distance for the placement observation. Number 3 is determine vibration frequency via light displacement. Apply different frequency to speaker to induce vibration. Track the oscillatory motion of the laser beam reflection. Measure frequency relate displacement pattern on the photodiode. Last, compare the laser displacement with theoretical frequency calculation. Lastly, verifying amplitude using different frequency and screen distance. Adjust the speaker frequency. Observe how different vibration frequency affect the laser reflection displacement. Modify the screen distance to investigate its effect on measured displacement. And compare observed result with expect amplitude variation across a different condition.
Hello everyone, now we move to the data analysis. For the first one, we focus on distance of 30 centimeter. So as you can see here, we use 4 frequency, which is the first one is 120 Hz, second one is 140 Hz, third one is 160 Hz, and the last one is 180 Hz. So we use this frequency until the last distance that we took the data. The next one is the distance of 50 centimeter, which is you can see here at 120 Hz. The peak is not really accurate because of the photodiode is not working well. And the second one is 140 Hz, you can see that the graph is sinusoidal, which is the wave of the graph is very in a good condition, and 160 Hz, also 180 Hz give the same graph but at a different amplitude. The next one, for distance 70 cm from 120 Hz to 180 Hz, we have a problem to get a normal and good graph and data because of some error during the experiment that related to the photodiode. What I can tell you here, the photodiode is not working really well. Now is the distance of 90 cm, 120 Hz to 180 Hz. As you can see here, the graph given there on the oscilloscope give a little bit different with the previous one. So now this is the data from the oscilloscope that we compare with the exact one, which is 120 Hz to 180 Hz. So from the reading of oscilloscope, what can I tell to all of you, that for example, the exact data that we use is 120 Hz, but on the oscilloscope, the frequency appear there is double or triple from this origin value. So for the data of 120, the exact data that really accurate is at 50 cm. For 140 Hz, as you can see here, the exact value that accurate to the origin is at 30 cm. The next one is 160 Hz. As you can see here, at 70 cm, the value is 161.30, and the last one is 180 Hz. There is no exact value, which is we can assume it between the 79.36 and 303.0. Okay, so now we move to the discussion of this experiment. So what can I tell to all of you, that our experiment is not really successful to detect vibration using a laser and photodiode, because of the data is not really in our expectation because of changes in reflected light intensity. So the result from our experiment is very causing vibration measure in a dark room or use limitation. We got a short time and face main challenges involve alignment issue, insufficient vibration amplitude, and also external signal interference. From running this experiment, what can I conclude is the photodiode is really sensitive with the high temperature,
validating the theoretical basis of optical vibration sensing. Varying frequency and screen distance helps verify the relationship between vibration
So from this experiment,
vibration in bridge,
it
tower, and
provides us a
building.
useful experience
Seismology
in handling
measures subtle ground
detection
thermal and
system
seismic activity.
and highlighted areas for
Precision
future
engineering track
improvement,
fine
so
mechanical
that we
moves in
can
delicate
get
machinery.
actual
biomedical
data
setting,
that
and
we want and the actual graph that we
invasive
need.
monitoring of biological vibration, for example, pulse or vocal cord vibration.
Thank you for watching.